All right. So today we are going to be talking about energy. Again, you will notice I am still using these mind map notes. I think this is a great example of how to use mind map notes when we're talking about how things are related. So you can kind of start to see from these notes on energy that there are many things related in the field of energy. So today we're going to be talking about what energy is and how to calculate various types of energy. That is our objective for this video. Our essential question that you all should attempt to answer in about a 1 to 2 sentence summary at the end of your notes is, what are the different types of energy and how can they be calculated? All right. So if we are zooming in on energy here, let's start off with very simple, the definition of energy. And I will get my highlighter tool out. So our definition for energy is the ability to do work. Again, very, very simple definition. Energy and work, which you all learned in the last video, are related, and we will talk about why in one of our upcoming videos. Energy is, just like work, also measured in units of joules. So when we describe an object's energy, we're going to use the unit joule to describe that object's energy, such as this ball rolling down a hill has 10 joules of kinetic energy. And we'll talk about what that means in just a moment. But that's your pretty simple definition of energy, the ability to do work, and energy is measured in joules. Now, when we talk about energy is a scalar. So it is a scalar quantity. It does not have a direction. So unlike force, unlike acceleration, velocity, momentum, these are examples of vectors. So as a reminder, vectors, they do care about the direction. So force has a certain strength as well as a direction, right? We know that this bottom arrow is going to be a smaller force to the right than the arrow up top. So vectors have a magnitude and direction. However, energy is not a vector. Energy is a scalar. So a scalar does not have a direction. We only care about how much energy an object has. We don't care about what direction that energy is going. We also have different types of energy. All right, so there are many, many different types of energy in our universe. We have thermal energy, which is typically, we see that if you're holding a hot mug of hot chocolate or tea or coffee, that's thermal energy being let off. All right, so it's heat, it's warmth. That's what we talk about when we talk about thermal energy, and we will get into that maybe at the end of the year. We also have electromagnetic energy. All right, this is when we talk about the electromagnetic spectrum. If you've ever used a radio, in your car, we use radio waves to be able to listen to music or listen to podcasts and talk shows on our radio in the car. We use microwaves. Those are that's an example of electromagnetic energy to heat up food. All right, so those are all examples of electromagnetic energy. We also have electrical energy, which you will see in electricity. We have chemical energy. All right, when we eat food, that gives us energy. We want to eat food in order for our bodies to have energy. Our bodies convert food that we eat to chemical energy for us to be able to operate. All right. And then we also have nuclear energy. Nuclear energy would be examples of the sun. The atoms in the sun are constantly colliding, and there's a lot of nuclear energy there. There's also nuclear energy in atoms around us. So we may have time to get into nuclear energy at the end of the school year. But these are just a couple examples of different types of energy that you might have heard of before. The main type of energy that we are going to talk about today is mechanical energy. Now, there are two types of mechanical energy. There is, so again, this is our big one that we will be talking about in this video today. There is kinetic energy, and there is also potential energy. So you might be familiar with these types of energies. You might have heard them before. Kinetic energy is the energy of an object due to its motion. The variable for kinetic energy is a capital K-E. You might have seen other variables used for kinetic energy, but for our purposes, we are going to use the capital Ke for kinetic energy. The equation for energy, or to calculate kinetic energy, is going to be 1/2 times the mass of the object times the velocity of the object squared. So this is the mass. Remember, M stands for mass in most cases. And V is our velocity. So again, to calculate the kinetic energy of a moving object, you would multiply the object's mass times 1/2 times the velocity of the object squared. We also have potential energy. Potential energy is the energy due to position. Now, our variable for potential energy is PE instead of KE. And our equation is the mass of the object. I'm going to fix that A. Mass of the object times the acceleration due to gravity, right? Little g, which is negative 9.8 meters per second squared, times the height of the object. Now, what we are getting at when we talk about energy due to position, we're thinking about the energy of the object according to where it is and what its height is. So if we think about a ball having a certain amount of potential energy, a ball that has a height of 2 meters off the ground, I'll draw that here, has a little bit less potential energy than a ball at a height of 4 meters off the ground. So, and we know that using this equation, M times G times H. That's how we get our potential energy. It's the energy due to position. It's basically the energy that's built up according to the height of the ball, right? So the ball has this potential to fall, and it has the potential to fall a certain amount of height. And that height is what determines the energy, the potential energy of this ball. All right, so that is the main difference between kinetic and potential energy. Main thing to remember is potential energy. This object is not moving. It's pent up. It's all built up within that object, but that energy is not being released in the form of kinetic energy. Now, once that object starts moving, that's when the energy of the object becomes kinetic. So again, kinetic energy only refers to objects that are moving. Potential energy, that object is not moving. Now let's work through a quick example problem here. I'll zoom in a little bit. So in this example, a roller coaster goes down a ramp at a velocity of 10 meters per second. If the roller coaster car has a mass of 200 newtons, what is its energy? Now, a couple things to note. I'm going to be thinking, since it has a velocity, it is moving, right? Things can't move without a velocity. So I know that this energy that I'm likely going to be calculating here is kinetic energy. I'm going to write has a velocity. That's how I know that I'm going to be looking for the object's kinetic energy, because that object has a velocity. Now I'm going to work through these 4 steps to solving a physics word problem. First step is to draw a picture. So I'm going to draw the little roller coaster car. Here's the roller coaster. Roller coaster car is going down its ramp at a velocity. I'm going to redraw that V of 10 meters per second. The mass of the roller coaster car with all the people in it, it is 200. And I just realized I put the wrong unit for mass. So I'm going to fix that right now. The mass is going to be 200 kilograms, not 200 newtons. So I will fix that on this problem, because obviously that could be a source of confusion. Okay, well, I don't know why this won't let me erase, so I'm just going to cross that out and write kilograms here. Okay, now that that is fixed, I've drawn my picture. I can move on to step number 2. Remember, step number 2, we are making a T-chart of what we know and what we don't know. So, a couple things. When we are looking for things that we know from the problem, I always just like to look for the numbers first. And the first number I see in the problem is a velocity of 10 meters per second. So I'm going to write V is equal to 10 meters per second. Another number I know from the problem is, just adjust my colors here. Another number I see in the problem is a mass of 200 kilograms. So I'm going to write M for mass is equal to 200 kilograms. Now, like I said at the beginning, the object has a velocity. So I know I'm solving for energy. And since it has a velocity, only one type of energy is referring to a moving object, and that is our kinetic energy. So we know, since it has a velocity, it has a mass, we're going to be looking to solve for the object's kinetic energy. So that is step number 2, making the T-chart. Moving on to step number 3. Again, we are solving for kinetic energy, so I'm going to rewrite that here. And I'm going to write my equation to solve for kinetic energy, which is 1/2 mv squared. Again, if you needed to see that, that is over here. Kinetic energy is solved by multiplying 1/2 times the mass of the object times the object's velocity squared. So we've got our equation set up. We can move on to step number 4, which is going to be plugging in those numbers here. I like to rewrite my equations to have the fractions be changed to decimal form. It helps me keep track of things a little bit better. But you do what's best for you. Just know that 1/2, all I'm doing is changing this 1/2 to its decimal form, which is 0.5. All right. Now I'm good to just start plugging things in where they belong. So, and I used the wrong color there. So I know I've got a mass here, which is equal to 200 kilograms. So I'm going to write 200 where it belongs in the equation for mass. I also know that I have velocity, which is 10 meters per second. So I'm going to plug in the velocity there. And do not forget, I am always so bad at remembering this. So please make sure you don't make the same mistakes that I do. All right. Make sure you include that exponent. Remember, we are following PEMDAS. So we don't have any parentheses, but we are going to tackle that exponent next when we are solving for this problem. So I'm going to go ahead and rewrite everything the same as it is, because we want to tackle that exponent. So 0.5 times 200 times 10 squared. 10 squared, which is the same as 10 times 10. Remember, there are two 10s. That's what the square means. All right. That is 100. All right. So we've taken care of that exponent. Now we can move on to this multiplication. So now we have 0.5 times 200 times 100. All right, so we are going to actually end up with our final answer of 10,000, right? And we know that because 0.5 times 200 is 100. We're taking the half of 200, which is 100, and 100 times 100 is 10,000. So we get a final answer of 10,000 joules. Remember, our unit of measurement for energy, any type of energy, whether it's kinetic, potential, chemical, anything. Our physics official SI unit of measurement for energy is joules. So that is how we got our final answer there. And that is all we need to know about energy for now. So again, I know that was a lot of information. Please make sure you have finished completing these notes and written a 1 to 2 sentence summary about what you learned from this video. And I look forward to discussing this more in class with you all soon.